Well, I guess this is a good moment. All right, so as you know, today we have a seminar. The speakers are going to be our beloved PhD students who are going to basically update us with their progress in the first year of PhD. And the first speaker specifically is going to be Framarito. Yes, also I wanted to apologize for all the technical issues. I don't know exactly what was going on, but apparently it's more or less so yeah.
And don't forget to share screen.
Oh, the share screen. What was this?
The green one.
Ah, of course.
Yes.
Share full screen.
Yes, desktop one probably. Share. And that's it. So people online, can you see the presentation?
Yes.
Perfect.
Yes.
Right. Get away from
Yes, we can see it.
Okay. I can hear you better than the public. Well, hello everybody. My name is Francisco Arizo. I'm a PhD student here in CEFCA for around 1 year and 2 months, something like that. And I'm going to talk a little bit about the status of the PhD and what I've been working these last months. And well, my thesis title is the study of the environment on Galaxy cluster using J+ with different proxies. So well, here we have the index, I am going to talk a little bit. And well, the main thing is what are we going to talk about? The galaxy clusters and which is where are located the galaxy clusters. So we have to know the distribution of galaxies is not universe. It is not uniform in the universe. It has like a cosmic web, like has basically 3 components. Like the clusters, like is a concentration of galaxies and dark matter. The filaments that are these galaxies and dark matter that links with different clusters, and the voids. There is a lack of dark matter and galaxies. So the main question is what are galaxies made of? Big numbers, between 3 and 5% are galaxies, baryonic matter. To be considered a galaxy cluster, must be the number of galaxies must be around from 100 to 1,000 galaxies. Then we have the intracluster medium that is around 10–12%, and then we have dark matter. Here we have a nice picture of J+ survey, a galaxy cluster in the middle of BCG. This is the most brilliant galaxy of the cluster. We also see the intercluster mean and the intercluster light. So continuing to know what is a galaxy, what are the components, distribution. Here we have a nice picture of galaxy clusters MAC 00723 from JWST. And we have this structure of the galaxy cluster. What is a galaxy cluster? Well, as I said, is a concentration of galaxies that are bounded gravitationally in a dark matter host. So the main components are the BCG that, as I said before, is the brightest cluster galaxy. That is, if the galaxy cluster is relaxed, is in the center. Then we have the intracluster light, that we see this diffuse light that is mainly hot gas in form of plasma, and also stars. And well, of course, if it's a galaxy cluster, we need to have these galaxies. Here in this circle, we can see some galaxies. The main galaxies of this cluster are here, the white ones. And we also can see distorted galaxies that with the distortion of these several galaxies that we can see in the galaxy cluster, we can measure or have an estimation of the mass, of the total mass of the galaxy cluster. So I'm going to talk first about this, how to observe them. There are in the wavelength range, there are three main approaches that are in X-ray to locate the BCG and the hot plasma, as we can see here with the profile. In the optical to see the distribution of the galaxies, and in the millimeter when the Seldovich effect, that is basically inverse quantum scattering by the photons in the CMB, that when they interact with the hot plasma, with the plasma, the hot gas in the galaxies from the galaxies, that makes a boost of energy and makes a footprint in the CMB, and we can locate it and study these galaxies. So, well, what is this all about? The study of the environment of the galaxy cluster. So we have to know which the main question is how the galaxies evolve from the blue galaxies that are star forming to red galaxies that are quenched. So quenched means simply that the star formation stops. So basically there are three big groups. This is the nature versus nurture. It is basically the mass quenching versus the environment quenching. I'm going to talk a bit very fast about the mass quenching. It's simply related to the secular evolution of the galaxy itself by means of AGNs, galactic winds and supernovae. And we are going to focus more in the environmental quenching. So how these galaxies evolve have been quenched by the interaction with another galaxies. Mainly is about run pressure stripping, when the cold gas is stripped from the galaxies, or starvation. That is that the main hot gas of the galaxy is being stripped by the interaction of other galaxies, the intercluster light of the galaxies in a more dense environment, that is the galaxy cluster. So how to study all this? How to approach this study? So what we are doing now, and the main approach of this kind of studies, is to compute the stellar mass function. And the stellar mass function is simply counting galaxies. Don't forget that we are in galaxies, not stars. So this is the stellar mass function of the galaxies. We need to count the galaxies. The main idea, we need to count the galaxies in a volume and being in stellar masses. This the main idea is easy, but to do it properly is not straightforward, as we were going to see. What is important, the SMF is also exactly observable to study the galaxy evolution, and it's important also to the hydrodynamical simulation, to constrain the hydrodynamical simulation. Here we have the main idea of the SMF. Here in the right we have the Massin et al. SMF, and in the upper part we have the total mass, the total number of galaxies, both population red and blue, and below we have the separation between red and blue. And in the figure on the left we have like how we separate or the main two population of galaxies. We see the red sequence in the upper part, and the blue cloud in the upper part. Later, also we have this green part, but this also galaxies that mainly are going from the red sequence to from the blue sequence to the red sequence when being quenched. So talking about the G+ survey, you all know everybody how it is. It's around it's around 1600 G+ fields observed in 12 optical bands, narrow and wide bands. So we have a lot of slicing, so we can make a lot of statistics. So the next step is to download the data. So mainly in this study, we are in a range of redshift between 0.05 and 0.35 because of the limitation of the survey. And when we have downloaded the fluxes, the photo set, and the star gal class to know which are stars and galaxies. And well, we obtained like about 5 million objects. So now the question is, to compute the SMF, we need stellar masses. We don't have it, so we have to compute them. So we have this software very famous, SIGAL, that is simply and very complex. Is to fit with the values of the filters of the fluxes of each filters to make a set fittings, and then we retrieve the stellar masses. We also retrieve the color the rest frame colors and other magnitudes like star formation rates and other things. And here we have some results. We have millions of galaxies. This is two good results. So, well, SIGAL builds models. We have used these 6 models, basically stellar formation history with a starburst delay, stellar formation history delay with a starburst, stellar population of Roussel and Charlotte in 2003, nebula emission, attenuation loss, dust extinction, and module of AGN related. Here we have in the left part a seed of a star-forming galaxy with a cutout of it, and in the right part we see a set of a quiescent galaxy that has no formation of stars. So now the question is how we split these two populations in quiescent and star forming. There are several approaches. We have done several approaches also, but the main approach is to make the UVG diagram. But in our case, we have focused in the far UVG diagram because it's more separated both populations. But we are also struggling with that because comparing with the literature, as we will see later, the SMF isn't. We have to. There is like a lack of population of quiescent galaxies. But the thing is that if we use the specific star formation rate to divide, that is used like in leisure, with the separation in -10, we get good results comparing with the literature. So to compute the stellar mass formation, we need to do it quite properly. Before focusing on the galaxies clusters, we have to make a study to see which are the stellar mass function of all the galaxies in this redshift range, to have a look what is going. So we make first the stellar mass formation, the stellar mass function with all the galaxies from J+ in that redshift. And as I said, it's not only like counting galaxies, it's a little bit more complex. The main problem is to avoid or to take into account the Malcolm's bias. This is called, it's simply that the faintest galaxies are only seen in reduced volumes, and the brightest galaxies are seen in all size of volumes. So for this, the normal approach is the Vmax method. This approach is specifically by Pozzetti et al. The algorithm, and to compute the mass completeness. As we can see in the left picture, first we obtain to compute correctly the mass completeness, we sort what we can see here, all these galaxies of our study. The x-axis is the redshift, the y-axis is the stellar mass of each galaxy with all the distributions, and to correct from to do the Vmax method, we first need to compute the mass completeness. So we sort in magnitude, we select the 20th faintest of in each redshift beam. We determine the mass below lie the 95% of faint objects. This is, I mean, could be a little bit messy, but we have these points in each redshift beam, and the thing is that we fit these points to this different population of star-forming galaxies, quiescents, and all galaxies, to have a look of all of this. The method continues. We have to invert this function, obtain the max redshift of each galaxy at that volume. That is the minimum of the maximum of the redshift of the sample, and the maximum of the redshift of each galaxies in that mass. And well, we get these results. We also have this cumulative histogram to have a look of how is the distribution of the galaxy, of the masses of these galaxies. So we can compute well with all the sample, or we can make different subsamples in around 10.5 with a good completeness. So we have here the first results. We have 5. Okay, perfect. We have here the first results. We have compared with a lot of literature. Here is some examples. We have more comparison with more literature, but we have thought that it would be easier to follow and not be too messy, to compare our sample that is with lines with Mazen et al. 2013. 2013. The question and the difficulty also is to obtain also studies literature with the same redshift of our students. So we have to manage this, and this will be in the thought for future work. So we have here finally the SMF of all J plus in that redshift that we have selected, and we see that basically what it is thought that the quiescent galaxies dominate at high masses, and that the star-forming galaxies dominate at low masses. If we compare with the literature, we see that we don't have errors. So the thing is that above 11 and 11.25, the errors are going big. So this separation would be due to that. And finally, here in the left, we have here in the right, we have compared also with the paper of Vilea 2021. It's a study of the SMF with also J plus, but in the very near universe. I think it's 75 megaparsec, something like that. And to compare it and to know which are the limitations. So what we are doing right now is doing the star mass, the SMF, but now in the galaxies from the cluster and the field ones. So here we have a nice picture on where we have the red galaxies are belonging to the cluster galaxy clusters that are cross-matched with red matter. That is a survey of clusters in the red segments. And in the blue parts are the field galaxies that are with a cluster-centric separation between 3 and 4 megaparsecs to know which are the difference and to compare them. And well, this is work in progress. So the thing is that all these methods that we have computed for all the sample with J plus DR3 is more complicated than when applied with clusters. So we have to redo a little bit of the code, but to have an idea of what is going on. I know this is basically the summary and the future work, and that's what we're going to continue also to discuss and to know how to separate correctly, to study the environment with different approaches like cluster-centric distance, local galaxy density, and in the future with host arrow masses. And that's all.
You show that in the previous plot, yeah, here. You're detecting less quiescent galaxies at low masses. Do you think this is a problem of the fitting, or it's a problem of
completeness? Yes,
completeness.
it's a problem of completeness, I think so.
So these works go deeper, and that's why they.
Yeah.
But
So we're studying.
the data one is also J class.
Yes.
In that one, it's the purple ones are the quiescence of data, and that goes flat.
Yeah, but it's
It's 1 point.
it's
Yeah.
0.01. Is the word sheet.
Okay. So it's lower actually.
Yeah, related to that, I was wondering, because it can be due to the redshift range you're considering, no?
Yeah.
You find the literature and views were more similar to yours?
Yes.
Like, did you check in red? Maybe they do also narrow redshift for their mass function.
The thing is, we struggle with that, and we compare with a lot of literature, but it's also that maybe that comparison it was not good fitted because of the galaxy sample or something like that. But we have a lot of more comparison with literature. This thing is more like what we just compare with Massimidal, but yes, it's a issue to compare with different redshift bins, and we're working on it.
And is there any reason why you stop your selection at 0.25? Why don't you go up to 0.5?
I think it's for the limitation of J plus. So we have the quality of the data, and that redshift is there's a big dispersion when we're trying to separate the red sequence. And
asking about the limiting redshift, why don't you go below 0.05?
yeah. Because it's this case of the study, we decided it's at low redshift, but it's not exactly in the local universe. It's like
I do have a couple of questions myself. I'm a complete foreigner to this subject, so please bear with me. So in Seagull,
yeah,
you have to establish some models,
yeah,
for the kind of galaxy. So how does it work? You put
Western.
those models, and then Seagull chooses which model is the most suitable for each galaxy, or you have to previously know more or less which one of the models is going to work best.
No, it makes a grid with parameters with
Uh-huh.
these modules that I said, and it retrieves the best set fit with the less chi-square. Something.
All right. So then my question would be like, I guess you have a good reason to choose these models versus other models.
There are well, basically we talk with Juan, and it's the most used. The most to it.
If one, it's fine.
Yeah, try to carefully in the.
I don't know.
Yes, well, so some parameters, it doesn't interpolate in the grid. It has some Bayesian estimates for some parameters. But when you pick the best fit model, this is a model, it's not an interpolation.
And then my second question is that I'm a bit puzzled by this sky distribution that you show with the red and blue galaxies that are outside, that are field galaxies. I see a crazy selection effect there. Like, why? So like, I don't understand this. Like the field galaxies are basically these
Are
little-
galaxies
Uh-huh.
between 3 and 4 megaparsec from the galactic center of each
I missed the.
at each redshift of the galaxy cluster. So we see different sizes of
I thought that they were just field galaxies, farther than 3 megaparsec away, and I was puzzled by not seeing like.
the blue ones are, well, we consider them field galaxies or galaxy clusters. They are remote also this all these galaxies that could belong to both clusters, and we retrieve only this.
So like the white regions between the clusters, are they also considered field in your method? Because we would assume they are field, right? The ones
Yeah,
in
for ours,
between the
that's
blue.
Exactly.
Between these ones, for example.
Yes, or the larger, yeah.
No, because this would be more than 4
Claro.
megaparsec away. That was my question.
Our definition for field galaxies is
That is
between 3 and 4
it's
megaparsecs.
here.
Why not infinity?
Do not get contaminated with another cluster, so galaxies that don't belong without galaxy cluster.
Well, you already discarded them from the other clusters, right? So
No,
Because we might be missing clusters, is that you're missing clusters and you're.
I take into account this is photometric. So if it was spectroscopic redshift, you make it sure that they belong to the cluster and they are not included. But as this is photometric, we try to avoid contamination from other clusters. So yeah, in the middle, we don't have like information. So this is the easiest way, and for the field, we want statistics. So far, this is like a test. 3 to 4 is just to make the first test. The idea would be to do in some concept a cluster-centric distance. So this is kind of picking 2 cluster-centric distance, the 4 and some at 3, 4. But in the future, that will be like a continuous that we will go up to, I don't know, 5, 6, 10 megaparsecs.
So maybe we want to call slices. Maybe if you call it circumcluster. It's interesting.
And related to that, also in the figure where you show the mass versus redshift, there's a very important effect of discretization in the redshift, right? I guess you didn't complete the photosynthesis yourself, but
what?
yeah, in the next figure, in page 14,
This one.
the redshift distribution is not complete.
Yeah, it's discrete.
I guess it's for the photosynthesis,
Is the photosynthesis, yes, right?
but first I'm surprised that it's so discretized.
Yeah.
Yeah. And secondly, I wonder.
You can be photosynthesis by moving a grid of flexibility.
More grids.
But that increases your computational cost. I mean, if your uncertainty is going to be like 2%, what is the point of making a much more than that?
So it is some
That is
Gaussian
different.
You can blur them.
It's
okay?
But each of these groups has a probability distribution function. I would guess all of those, in fact, they do have their error one, which in fact is the probability distribution function.
Some last question? Or if not, let's thank, Don. Do you have your presentation?
Yeah, I
with you?
have in hello everyone, I'm Sepide Skandarlu. I start my PhD from 15 January of the 2022, and until now I will present for you how much my PhD had progressed. My PhD title isn't about the PSF. And I want to show you why now we are working on a PSF. My PhD title, my thesis title is about the circumgalactic medium in a local universe with J plus and J plus. When I came here, I start working with the J plus on a detection of the galaxies in a crowded region. But the main question is why J plus and why the crowded region? I selected J plus because we have a 56 filter and it's allow us to looking for the photospectral features of the object. And why the crowded region? Because I'm going to looking for the local universe galaxies. The local universe galaxies foreground contaminated by foreground and background object. First of all, we should separate each object from each other, and then looking for the circumgalactic object. If we don't pay attention to this issue, we are going to miss the correct information of the circumgalactic medium. In some cases, it's contaminated by the foreground stars. We cannot study the stellar population of the circumgalactic medium correctly, and even though maybe we consider it mistakenly as a tidal feature object. Due to this, I select the famous